Welcome, everyone. Thank you very much for being here. My name is Eric Wall, and I am the chair of the San Francisco section of AIAA. And it's my pleasure to welcome you. We thank you for being here. We are, the AIAA is the United States' largest professional society dedicated to aerospace engineers and other adjacent technologies. And we do a number of different things. One of them, of course, is activities like this, both locally and more at the national level. But there are many other things that we do, and I don't want to go into too much of it right now because we're already running a few minutes late, but if you want to hear anything more about it, please come and see me afterwards, or any of our other council members who are here. We've got Rick and Thomas and Nick and Sina. And where's Krishna? Oh, there we go, Krishna down there. And oh, we got Todd up there. So anyway, it's my pleasure to introduce you, Dr. Mark Tischler. Dr. Tischler heads Tischler Aeronautics with a focus on providing engineering support in rotorcraft and aircraft flight dynamics and control. He retired in January 2021 after a 38-year career as a U.S. Army senior technologist and senior scientist at Montefiore, California. For over 25 years, he led the Flight Control Technology Group that conducts handling qualities, flight dynamics, and control research on a wide range of fixed wing and rotary wing aircraft, and also on unmanned air vehicles. Dr. Tischler has been involved in numerous flight test projects in both his industry and government career. Dr. Tischler has published extensively in this field, having authored or co-authored over 200 research publications. He is the author of 3 widely used books, Aircraft and Rotorcraft System Identification, Engineering Methods, with flight test examples, Practical Methods for Aircraft and Rotorcraft Flight Design, and Advances in Flight Control, which you've got samples of here, right? Yep. So if you want to take a look after the talk is over, feel free to come down. Dr. Tischler has received many awards, many major awards for his work over the years, including being named the American Helicopter Society's Technical Fellow in 2007 and Nikolsky Honorary Lectureship in 2020 for lifetime career achievements in rotorcraft flight control. He has the rare distinction of twice receiving the Presidential Rank Award for Distinguished Senior Professional, the highest recognition presented to public officials. Dr. Tischler received the Department of the Army Distinguished Civilian Service Medal in 2020, the highest award that may be bestowed by the Secretary of the Army for extraordinary contributions as a senior research scientist. He received his BS and MS in aerospace engineering from the University of Maryland and his PhD in aeronautics and astronautics from Stanford University. Please help me welcome Dr. Mark Tischler.
Thank you. Good to speak with you. I want to thank right up front Eric Wall and Mohammed Ruby for inviting me to present here, and I know that there's a pretty large audience signing on across the United States and Europe as well. So it's a great honor. I'm going to get right into it, so we're a little bit late. And this presentation is based on my Nikolsky Lecture, and it's a traditional to indicate the connection to Professor Nikolsky, for which the award is named. My advisor was Professor Curtis, very well known in the area of flight dynamics and control. He developed the principle of long track. He was my role model. And as my own advisor, Professor Bryson, he used to say that a student of a student is a grand student. So I'm the grand student of Professor Nikolsky. This is an outline of my presentation. I'm going to be marching through this as I go, so I won't walk you through it here. The first topic is going to be rotorcraft flight control drivers and technology. What makes rotorcraft special and different from the fixed-wing counterparts? A number of things. First of all, rotorcraft are high order, they're highly coupled, there are multiple dynamic systems that are dynamically coupled to each other. The aircraft has a lot of pitch roll coupling, so it's not a single input, single output system at all. It requires the engineers to have a broad multidisciplinary expertise to understand how these things work together. the aircraft is highly unstable, and it has significant time delays. As a result of all this, if you look at it in terms of a Bodie plot, we see a lot of these. This is the roll response, and what you can see is that the rotor dynamics and the fuselage dynamics are in the same frequency range. And what that means, if you look at it in terms of a root locus plot, you have a second order system, which represents the fuselage and rotor dynamics. And if you ignore the time delay, you think that you can close the loop very tightly, but in reality, there's another mode here called the lead lag mode, and there's a lead lag mode, and even for small amounts of time delay, the rotor will go unstable. So what that means is we need accurate models to do the design and development, and we need transparent design and development methods. So let's talk about 4 major areas of technology development over the last 50 years. Okay. First area is handling quality development, and a good reference for this is in a Nikolsky paper by Professor Patfield. And handling quality is basically handling quality specifications basically define how you want the aircraft to fly to give you good response characteristics. And so fixed wing folks came up with an update to their spec. It's called 8785C, and that was developed in 1980. And one of the big innovations for them was they moved from the time domain to the frequency domain. And so in the rotorcraft area, we did the same thing, and proposed that we moved all of our specifications into the frequency domain. We had a lot of collaborative partners. The aircraft there is shown on the right, and ADS-33 was released after 20 years work. So it was a very long process, and then the flight test guides that came along. And ADS-33 was a huge breakthrough because it provided design guidance for folks like yourselves wanting to figure out how should the aircraft fly, how should it fly, so that the pilot or control system will like the way it's operating. And so one of the first hurdles was moving into the frequency domain, and there were a lot of folks that questioned whether frequency domain characterization was applicable and practical. And so I was the first one to actually do system identification in the frequency domain on rotorcraft. It had been done in fixed wing, but not before rotorcraft. And the first application was a flight testing I conducted on the X-15, and then following on the Gulf 214. And what happens? You do one of these frequency sweeps. This one's pilot generated. It can be computer generated. You get another one of these Bodie plots. So you have magnitude, phase, and coherence. Coherence tells you about linearity, and what it shows you is that the aircraft over a very wide frequency range is highly linear. So that means the input to output response is quite linear. Now, they may have local nonlinearity, but if you look at it from the standpoint of a dynamic system, it's highly linear. And not only is it highly linear, but even though it's got a lot of dynamic modes, you can represent over a very wide frequency range with just a simple second order transfer function. And when you do that, and you look at it in the time domain afterward, you can see that the prediction is very, very good. In the top right there, it tracks, the model tracks that it's flight data very good. And then you basically take this Bodie plot and you can pull off some of the specification parameters like the bandwidth and the equivalent phase delay and so forth. These are how you specify the aircraft response characteristics. So this demonstrated that we could use frequency domain characterization, and that's in fact how all handling qualities are represented now. And the frequency sweep flight test manual told the flight test community how to do these tests in a safe way. Okay, the next major area that we had to tackle was understanding the effect of time delay. And the effects of time delay were very well known in the fixed wing community, and there was work published that shows that if you have about 120 milliseconds of time delay, the handling qualities start to break down. What we're after is a Cooper-Harper rating. This is a rating given by the pilot, Cooper-Harper rating of 3.5 or less. Yeah, that's called level 1 or good handling quality. And if you have large amounts of time delay, the handling quality degrades. The pilot is not able to fly it well, and he gets into what's called a pilot-induced oscillation. Well, the very first fly-by-wire aircraft is one that I worked on, and it's called the AIAA-SF, and it had very large time delays. And sure enough, every time the pilot would try to do a high gain or aggressive task like a slope landing or a run-on landing, the pilot would get into a PIO, pilot-induced oscillation, and lose control of the aircraft, and the aircraft would trip offline. So what that meant was we had to be very careful about these time delays. So they are really fundamental, not only to the feedback system, but also to the ability of a pilot to fly it or even an automation system. There are other people that came along in Britain to look at parametric studies of the effects of time delay. And then there was a very good study done collaboratively between the Army and Germany, DLR, which indicated that the break point for time delay was 120 milliseconds, which in fact lines up exactly with the fixed wing. So there, you'll see throughout this talk, there are many places in which the fixed wing people started, and then rotorcraft community came along, and there was a great deal of similarity. So as a result of this, the spec. So here's one of these specs that I've been talking about. So for example, you pull off the bandwidth, which is the point at which the curves roll off versus phase delay. And initially it allowed for very large time delays, 200 and 300 milliseconds. And eventually it was capped at 120 milliseconds, just like the fixed wing and the rotary wing folks did. So that you'll see throughout my talk that effective time delays are a big deal. They arrive not only because of the time delays, but for example, in the digital system, they're in fact not the largest sources of time delay. The biggest sources of time delay are things like the response to the rotor RPM, if you have one of these air taxis we're talking about, filters and the actuator, especially the actuator rate limit creates a very large equivalent time delay. The next area, which was very important, was understanding the effect of disturbances on the aircraft response and coming up with a spec which could define how well the aircraft rejected disturbances and how it's positioned in space. And what we used for this was the classic sensitivity function of 1/1 plus GH, which is what you learn in fundamental control. And you basically put a sweep into the hold variable. In this case, it was the roll angle hold. So this is a control system. We're seeing a lot of, it's called a explicit monofollowing, and it basically holds the roll angle. And if you turn the gain up, you measure the minus 3 dB point, and that defines what's called the disturbance rejection bandwidth. And this is a very good spec for characterizing how well the aircraft holds its trim and returns to trim. So as you close the loop tighter, the curve moves across, you get more peaking, which means that it's starting to become oscillatory. And what happens then is the aircraft will turn to trim faster, but becomes more oscillatory. So the trade-off between speed of response and stability. And then there was a very nice collection of results developed by Tom Berger at the Army. And what he showed was that if you fly the aircraft in very common conditions, you don't need much feedback gain. You don't need much disturbance rejection bandwidth. But as soon as you fly these rotorcraft in turbulence, then what used to be a good aircraft, remember, it's super heart rate 3.5, becomes bad, and you can improve it to level 1 by turning up the feedback gains and making the aircraft respond better. So it turns out that this disturbance rejection bandwidth is a key driver for flight. All right. There we go. Oh, that's a good one. Yeah. Okay. So, there were a lot of aircraft have been designed to meet AIAA-SF, the design spec. You see a wide number of these, both in the United States and in fact, the very first helicopter, fly-by-wire helicopter designed to meet AIAA-SF was an H-90. If you go online on YouTube, there are amazing videos of this aircraft landing on a Navy ship. A European ship in a very high sea state, very difficult conditions. And they designed the aircraft to meet AIAA-SF, and it flew extremely well. So it turns out that not only military aircraft are using AIAA-SF, but it's also being widely used for commercial aircraft. So we'll see this as we go forward and start talking about eVTOLs, that these new aircraft will also be designed to meet the same requirements. Because this is really the only source of dynamic and handling quality requirements for rotorcraft. And now I want to talk about the next topic, which is physics-based modeling. And a good reference to this is Professor Pat Curtis and his Nikolsky Lecture. Physics-based modeling started out in the 1970s with what's called a tip path plane model, and Bob Chen's arm-top tip path plane is basically you model the rotor as a disk, and you write very simple equations for the disk in space. And this was a good starting point for not only for real time but also offline flight control design, but it was crude. And the next series of models that came along were blade element models. And blade element models, you basically segment the rotor into a whole series of small elements and sum up all the forces and moments. And the pioneer for this is a fellow named Jim Hallett from Sikorsky, that developed the GenHel program. And then Boeing came along and figured out how to linearize GenHel, which only initially was a time marching simulation. Eventually, these models included flexible blades, and after he did his work, then we actually linearized GenHel. There are many other models. Another one is in Canada, a leader in simulation and pilot simulation is CAE Canada, and many others. In addition to these models of the aircraft response, we also have to get models of how the aircraft responds to turbulence. And this is important because of the driving model, which is you probably learned about. It works in forward flight for fixed wing, and it works for rotorcraft in forward flight, but in hover it breaks down. And in fact, it blows up because it has velocity in the phenomenon. So we came up with the concept of a control equivalent turbulence model that basically feeds in turbulence, shaped turbulence directly into the actuators. And we've seen this a lot because turbulence is one of the main drivers for control system design and work. All right. The next major development was incorporation of higher order aero. So we started out with things like what's called prescribed weight, where you have the rotor shedding awake, and you can assume it has a certain form that makes it prescribed. And this allowed the researchers from the Technion in Israel to understand the angular cross coupling, which had to do with weight distortion. There are many others. There's a company locally in the Bay Area in Santa Clara, actually, called ART, Advanced Rotorcraft Technology. They developed a very widely used simulation model called Flight Lab. They've incorporated higher order aero called the vortex particle method, which we'll see in a little bit later. There's Charm from CDI. University of Maryland developed a simulation model that's also used with phenomenon called helium, and another one called Rapid. These are more and more sophisticated models. The problem is that there's a huge amount of uncertainty to the input parameters. You may not know a lot of the interference effects and those constants, and a lot of the theory does not correspond well to the configuration. So what happens is that you may have a great deal of a very comprehensive model, but you don't know what numbers to put in. In fact, inertias are rarely known to go within better than 20%. So really fundamental things like that you don't know well. And if you don't know those well, you can have, you can be calculating out with a fourth and fifth decimal place, but it doesn't matter because you get the wrong answer. Okay. So how do you judge the accuracy and fidelity of the model? Well, you use what's called system identification. System identification, which I showed you before, you do a frequency sweep. Here was a UH60. The solid line is the flight test data, and the initial simulation model from GenHel, which was the Sikorsky model, was way off, and it was off in the time range. You can see it there. And then slowly, as the models improved, the simulation response began to converge with the flight test data, and in the short term, the time response is also converged. So what we see is that simulation is that system identification provides essentially a very useful and reliable way to assess the fidelity of these models. And you really can't do it in a time domain. Originally, that's the way people would look at it, try to look at these wiggly curves and see how close they were. It's very hard to do. If you look at the frequency domain, you can look at it frequency by frequency. And it allows you to understand what the accuracy of the model is and whether you're improving it. The next area of simulation modeling I want to talk about is what's called a stitch model. So if you do the system identification, one of the results is that you can extract the state space model of the aircraft. Okay, so not only once you get the body plots, and I'll talk about this in a moment, you get stability derivatives, but you can also get stability control derivatives from a nonlinear simulation. You can have to do numerical perturbation and linearize the equations of motion. And basically, if you can build a lookup table in which the ABCD matrices are stored as a function of velocity, essentially several discrete points. You make a lookup table of the stability derivatives, of the control derivatives, of the trim data, trim arrow, and then all you have to do as the aircraft flies in simulation, you tell it what speed you're at and what your control is, and it calculates the forces and moments. It adds to the aero forces, the gravity forces and moments, and then drives the equations of motion. And this is very effective, and it's very widely used now as a way of building simulation models when you don't have a physics-based model. So what a lot of companies are doing, and I'll talk about this more, that companies like CAE and NRC, they just instrument the aircraft, fly it, get system ID results for several point conditions, and then build a lookup table and interpolate it. So these are called quasi-linear parameter variants. So basically, they're linear at the anchor points, but then you're interpolating between. And we developed a tool called Stitch in the Army, which builds these for you automatically. One of the nice things about this is it allows you to do precise extrapolation for changes in mass, CG, and moment of inertia. So you don't have to test it for every one of those points. You only have to test it for 4 points, or basically 4 velocities at low altitude and 4 velocities at high altitude, and you can characterize the entire envelope of the aircraft and build an entire simulation. So here's an example of how accurate this is. This is using the general model in which we linearized it, and so we had essentially a truth model. And we flew the nonlinear simulation from hover forward 100 knots, turn back to hover, and then we compared that with what we would get by using one of these Stitch models, using these the linearized point models. And what you can see is that it's essentially perfect. There's a small offset in actuator, but all the dynamics are perfectly modeled. So you can represent these very complex systems by a very small number of point models, okay? And it works extremely well. And as I said, this is sort of widely used in development of training simulators, and it's really ideal for UAVs because UAVs are changing so rapidly that it's much easier to go out and fly it, do system ID, and build yourself a look. There's a lot of work that in a working group that I led over a 4-year period, which involved multiple NATO countries and a wide variety of aircraft, looking at how to assess the fidelity of the simulation models in the frequency and time domain, and then how to figure out how to improve them. And if you're interested in this topic of figuring out, okay, how do I assess the fidelity? This is a good open literature report. You can Google it, find it online. And it goes through a variety of methods from very simple to very complex, explaining how to assess and update. I want to switch now and talk about system identification. So I've introduced you a little bit to what it is, and a reference to this is my textbook on the topic. System identification basically has you excite the aircraft, measure the excitation, the control, the actuator input, and the aircraft response, and it basically extracts equations of motion. That's what system ID is. Okay. System ID came along again. Fixed-wing people had a big jump on us at NASA by 2 pioneers called Idleton and Main. At NASA Dryden, they developed a method in the time domain called MMLE. This was later applied to Rotorcraft in the time domain by Malusis from Sikorsky, and then and others in Germany and in industry. And then I came along in the 1980s when I joined the Army and was the first to use frequency sweeps, and I developed a method called the frequency response system identification method, and applied it initially to the F-15, and then many other aircraft, including the B-105, and there are a very large number of aircraft for which this method has been used. and it's probably the largest single most widely used approach now worldwide. Hamill came along and led a NATO working group that I was involved with, which was a real breakthrough in which our team looked at 3 different flight test databases, a whole variety of system ID methods, and then we issued this report, which is also available in the open literature. And so if you want to understand system ID, my book is a good resource. And then if you want to see other aspects like instrumentation and other things that are going into great detail, great references. So I essentially adapted a lot of these methods from fixed wing, who had done frequency domain system identification for fixed wing, but never in rotorcraft, and I had to introduce a lot of innovations to make it work for rotorcraft. And basically, the idea is that you get these voting plots, which I've already shown you, and you get essentially a multi-input, multi-output frequency response matrix. Then we use an optimization algorithm to extract from that state space models, and then you check it in time domain. So that's the basic approach. It has a lot of advantages over the time domain methods which I talked about, and that is it works on unstable systems, whereas a time domain method, which in time marching will blow up because the aircraft open loop dynamics are unstable. All hovering vehicles are unstable, all rotorcraft are unstable. It also handles widely spaced modes, including structural modes, and it gives you a model that tracks the responses best in voting platform, which is really important for flight control. Because all flight control design now, whether it's CISO or MIMO, is all done based on voting. And so we embodied this approach in a tool called Cypher. It's really the only commercially available tool. It's widely used. It's about 60 sites worldwide. I have mentioned my textbook. I gave a course, 4-day short course for AIAA online, and if you're interested, that's available on demand. And the Germans have essentially coded up this approach in one of their tools. So here's an example of this. This is the Bell 407, which was an aircraft which was being developed for an Army program called the Advanced Reconnaissance Helicopter. And this is the pitch response, the unasked pitch response. And the data is the solid line again. Again, you see magnitude, phase, coherence. Coherence is very high, which again indicates the input to output map is highly linear. That's very important. Again, if you have a lot of local nonlinearities, but the input to output is very linear. Then you extract a state-space model. This just shows you one of the responses, but you typically have about 36 of them in total, 409 outputs. And you get a state-space model which tracks that. It agrees very well in the frequency domain, and then you can check it in time domain. And what's really important is, you can see here, is that these are large responses. We're talking about maneuvering flight plus or minus 20 degrees per second. So this is not small perturbation motion. This is maneuvering motion. Okay? And so this approach to extracting models is very, very useful. You can also use it to validate your control system. So in this case, we just represented the equations of motion as a 6-degree of freedom, just your classical equations of motion, and we represented the rotor as a simple time domain. And that worked out fine, and this led to significant reduction in the development of the AIAA aircraft. That doesn't work when we have highly agile aircraft. And remember the B105 example I showed you at the very beginning, which has a couple roll and flap dynamics. And when you have that, this simple model structure cannot track the inflection state. You have to go up to a higher order one, which represents the rotor very simply. And so first order dynamic lag. We also include some of the other characteristics. And when you do that, you can then extract a model which tracks these more modern, highly maneuverable rotorcraft extremely well. The same kind of approach can be used when you have structural dynamic systems. And Nanda's here and a lot of experience. This is flight test data from the Boeing 777 that we flew with them. There's no scales because it's proprietary data, but what you can see is the excitation of the first wing anti-symmetric bending mode, which is a primary mode for roll control. And I proposed a model structure called a hybrid flexible model, which basically allows you to merge and combine the equations of motion for the structural flexibility with the rigid body equations of motion into a single set of equations, and then you can use this modification to track that. You can also use the same approach to combine mass trend models with rigid body state space models, which is very useful because typically mass trend models work at high frequency where you have structural dynamics, but they don't do very well at low frequency, and the rigid body equations work at low frequency, but they have no structural dynamics. So this approach allows you to merge the two sets of dynamics and use. All right, so now we have very accurate models. Okay, so now what do we do with it? Well, now we want to design a flight control system, right? And for that, there's a textbook that I wrote with my team at the Army, and this is a useful reference. And we talk about development of flight controls. All right, so once again, the fixed-wing folks were way ahead of us. They fielded the first digital fly-by-wire production aircraft in the F-18 in 1978. Boeing came along very quickly for Rotorcraft and flew a digital fly-by-wire on a demonstrator called the Model 347. And then the Army had a technology demonstration program called the ARDI program, in which they demonstrated advanced augmentation and side stick controllers. But the big breakthrough came with the development of explicit model following. Explicit model following is basically has a regulator loop, which is here, the feedback loop. You have a simple inverse model of the aircraft in the forward path, and then a command model. So basically, it rejects disturbances through the regulator loop, and then it predicts how the aircraft is going to respond and inverts it with this simple inverse plan. Now, people use nonlinear dynamic conversion. The downside of that is that the inverse shows up in the feedback path. And what that means is that if your inverse is wrong, it'll affect stability. And that's not a good thing. So they have to work very hard to get an accurate model, whereas we can use a more crude model, a lower order model. So this was developed by researchers at Ames and the German establishment, and allows you essentially independent design of the feedback path separate from the response to command. So that's a big deal. And this was worked out in flight in an aircraft called the AIAA-SF. And I showed you that earlier in the presentation when we talked about time delays. So the AIAA-SF was the first production representative fly-by-wire demonstrator. It's a big breakthrough. And it used explicit model following as a way of meeting these ADS-33 response requirements. It allowed for very simple and transparent design. It had a lot of advanced features, including advanced command models and pilot selection modes. And since this demonstration, explicit model following is essentially ubiquitous. I don't know of any fly-by-wire rotorcraft today that doesn't use explicit model following. And just I show it to you in here. And so this is a good. It retains a lot of the classical aspects of feedback control, but it allows you to easily set up the system to follow any of the specifications. So this is something that as students it's really good to learn about and learn to do. All right. Okay, there we go. The next step, once you have the architecture, is figure out how you drive that architecture to meet the handling quality requirements I talked about in the previous section, right? So we have things like stability margin, disturbance rejection bandwidth, speed of response, which is called bandwidth. We have all these specs, typically about 30 or 40 specs at one flight condition, and you want to drive your design to meet all these specs simultaneously. And a very efficient way of doing this is using optimization. And so the idea is that the user specifies the architecture, like explicit model following or something else. He specifies chooses the specs from ADS-33 and some of the other locations. And then you use Pareto optimization to essentially drive the control system to meet all the design requirements with a most efficient use of the actuator. So this is a very smart way of doing control system design, direct optimization. This method, once again, was developed on the fixed wing side, and it was developed in Europe for the Eurofighter, which was developed very successfully using this approach. And then I came along and led a long research activity that spanned about 15 years, and we developed a tool called Conduit, which is essentially a one-stop shop that gives you libraries of all these specs. You can import them. It's coupled to Simulink, and all you have to do is you tell it what your control architecture is. Could be LQR, could be H-affinity, could be explicit model following, or simple PID, and then you say, okay, what are the design parameters like feedback gains or Q&R matrices and LQR, and it will optimize the system to meet the requirements with the minimum amount of overtime. And that's a tool called Conduit. And that's, again, very ubiquitous. It's the only commercial tool of its kind that does direct optimization for a wide number of specs. That's really developed for aircraft applications. We've used it for aircraft and rotorcraft and UAVs and all manner of vehicles. Again, there are about 50 sites worldwide. It's in widespread commercial distribution. And I'll teach a course with my colleague Tom Berger in December through AIAA. It'll be available in real time as well as on demand. And again, textbook. Okay. So here's an example of how this works. This is it's called the K-Max aircraft. It's a very interesting machine. It's a synchrocopter. It's almost like an egg beater, two rotors that intermesh. And a very successful aircraft. And the Marines had a project with the Command Aerospace to make it unmanned and use it for payload delivery to the troops. And I worked with them, and my team worked with them, and we were given information about the actuators, saying that they were relatively fast, about 95 milliseconds. And when we put that into the design and they flew the aircraft was essentially obstacle. And we said, okay, what's going on? And the main uncertainty were the actuator dynamics. We used the specs provided to us by the manufacturer. So we measured it, and it turned out that the actual time delay was about 290 milliseconds. So it was huge, right? 200 milliseconds worse. Okay, so first of all, you never trust the manufacturer's definition of their actuator. So, but once you dial in this 290 milliseconds and we optimize the system and then we flew it flew beautifully. So what it says is that once again, just like in handling quality, it said time delay is a key driver. It's also a key driver for flight wire control system design, and it must be accurately determined from the system. So here's a real success story. The aircraft was fielded and operational for some years. All right. I want to talk about now how to combine these various technologies that I've been talking about, these four technologies, and show you one example case study, which is a great aircraft developed by Sikorsky called the C-53K. It's the first U.S. production fly-by-wire rotorcraft. And it's a very large aircraft that has a great deal of structural flexibility, so they needed to include the Nastran modes in their physics-based model, and then they use system ID to validate it. So here's their Gen Hill, including the structural dynamics, and here is the flight test data. You can see it's very, very good agreement. So once again, system ID provides you that truth data that you need in order to judge things as a function of frequency. So low frequency, it looks very simple, just a simple sort of first order, second order, in this case, second order response. And then at high frequency, you have all these structures. And that's very important for determining where to put the sensors so that they don't pick up the structure. All right, so the CH-53 was flight tested and fielded. And they flew it in a wide variety of conditions. It has a great deal of augmentation, all designed initially with Conduit, and they flew it in really difficult conditions. This is under the PVE called degraded visual environment, in which you're in brownout. You basically can't see a thing. The pilot has no cues, and he depends entirely on the control system to keep the aircraft flying well and flying right side up. And these are the same handling quality ratings I talked about. Remember, we want typically a 3.5 or less. And you can see that for all these various maneuvers, for all kinds of external loads, the aircraft does in fact meet these requirements. And that was by pulling together all these technologies: physics-based modeling, system identification, handling qualities, compliance, and advanced methods for flight control in one big success story. So there are many others, but this is certainly a highlight. All right. Now what I want to do is move from where we've been to where we're going. And I know that's a lot of reasons that folks are here and online. And I want to talk about a variety of different aircraft. The first one is that the Army's Future Vertical Lift. There are two classes of aircraft. One is a replacement for the UH-60. It's a controlled aircraft troop transport. And the replacement aircraft is called FLRAA. And the winner of the competition is Bell with their advanced tip-order V280. The FARA program, which is to be a replacement for the Apache, was in fact just canceled last week, unfortunately. We don't really know what the future is going to be, whether these prototypes will be carried on by the manufacturers. We don't know, but I have results which speak to these configurations, which are interesting beyond whether the Army picks them up and they may be offered for other competition. So let's just first talk about the results for V280. And so this is the aircraft right here. They did flight tests. They swept their system integration lab, which is essentially a hardware in the loop laboratory. You can see very good agreement. Again, magnitude, phase, coherence. This is the roll rate response. You can see that the physics-based model and the hardware in the loop simulation tracks flight data very closely. And you can basically take the difference between these two curves, you get an error function. And when you're within these boundaries, which are defined within that NATO report I mentioned, within these boundaries, you meet the requirements, and it says you have good fidelity. And then there's some squared cost function, and that also meets the requirement. So this validated the V280 model for flight control design and for handling models. The next application is the X2. This is a demonstrator of advanced rotorcraft demonstrator by Sikorsky. So it has a coaxial rotor with a pusher prop, drives it to go very fast. And there were two models, two physics-based models that were developed. Gen Health, I already mentioned, was the Sikorsky one. And then we had the helium model, which I also mentioned. And you can see these two models agree with each other, but neither of them tracks the flight test data. And what's really important is this is sort of the rigid body response. Then as you get out toward the rotor modes, which are really important for this kind of aircraft, because they're lightly damped and they're going to be important for the control system design, you're way off. And so what the researcher did in this case, Sikorsky and Army researcher Andre Juhas from my group, basically use optimization in system identification tool in Cipher to extract physical parameters, things like the equivalent hinge offset, the rotor inertias, the rotor flap frequencies, the fundamental sort of physical parameters that we didn't know very well. These are advanced configuration. We didn't know exactly what these physical parameters are. And so when you dial those back in and update the simulation model, you can see now that it agrees extremely well. And so this shows you a path for both assessing the fidelity in the model and for updating. And this is one of the methods that are described in that area. So we have considerable improvement using this approach. All right. Another approach was developed originally under a collaboration and then picked up under contract by ARC using their vortex particle method. So it's sort of in between a blade element model, a simple sort of F equals MA model, and a CFD. It's sort of quasi CFD. It doesn't run in real time. So this is the vortices being shed down by this coaxial rotor system. takes about an hour to run one of these frequency sweeps, whereas in real time it only takes about 90 seconds. But to actually run it in the computer, in the supercomputers, takes about an hour. So what that means is you can sweep the rotor, you can measure the vortices being shed, and then you can use system identification once again and come up with relatively simple models of the inflow, and that's what's shown here. So what we've done is extracted simple models of the air mass going through the rotor system. It has a certain dynamic response. When you change the collective, change the angle type of the blades, it's a certain amount of time to entrain the air mass. And there's also interference between the two rotor systems. So that's all captured. And then once you have that, then you can check the broken loop response. The broken loop response is just G times H. So it's the plant times the feedback compensator. And that defines floating margin, right? That's usually the gain in phase margin. And so the truth model, which you get from running this simulation for an hour, that's the black lines. Then you want to know, okay, what about now we've extracted an LTI model to run in real time and for flight control purposes. This is not going to be useful for flight control, it's just a time marching simulation. And so what happens is that if we look at the sort of state-of-the-art modeling assumptions, it's something called the Fit-Figures model, and it represents the interference in a very crude way. It doesn't agree very well at all. Produces a very high cost function. You want a cost function of less than 100. It's very high and very cost function. Then if you use these simple identified models, the cost function now drops very low, 24. And now your LTI model will track this sort of quad CFD very well. So it's a pathway to use advanced modeling methods to get to LTI models for the use of flight. And so this same approach has also been picked up by a company called CDI on the East Coast with their Charm freeway, and now Cypher is embedded within these two simulation environments and allows you to use advanced aero, but then lift out of the advanced aero these LTI models to be useful. All right, and then Tom Berger from the Army, now the Army Rotorcraft Technology Flight Control Technology Group Leader, has done a series of simulation experiments looking at high-speed rotorcraft handling qualities. And at high-speed, rotorcraft dynamics look a lot like fixed wing. So he said, well, let's see how well these fixed wing specs can predict handling qualities. And so if you look at these two aircraft, they're in the level 1 region in terms of the fixed wing specs, and then you flew it for a variety of different maneuvers, and sure enough, they're all in the level 1 region. So it proves out the adoption of fixed wing handling qualities for out of loop and in high-speed regime. So even though you may be working in rotorcraft, there's a lot to be gained from understanding fixed wing experience that we've seen. There's a lot of crosstalk between the technologies. All right. There are many additional highlights that I don't have time to cover, but they are covered in my written paper. Things like rotor state feedback and some advanced specs that were included in AIAA-SF, and a really cool demonstration of damage tolerant control when you have redundant control surfaces, which is very common on these eVTOLs. You have more surfaces than you have degrees of freedom. Right? And this allows you, if one of them fails, to reconfigure. And what Sam did together with Bisecting, one of the Rotorcraft companies, is demonstrated this ability to reconfigure on the fly damage tolerant reconfiguration with a scale demonstrator. So it's really cool. All right, but there still remains many upcoming challenges. We don't have the flight test results from these demonstrators I was showing you, the V280 and some of the other demonstrators that were developed. They're all proprietary, so that's a problem. We need to include this lessons learned in the mill spec, and also these the development schedules are really compressed space. There's this idea that we're going to let a contract and they're going to be fielded very quickly, and the only way that's going to happen is by minimizing the flight testing and the control laws using these advanced methods like system ID, like getting the right mill specs, having an accurate model. and then using a good design method. All right, let's go on to the next. And so before we do that, let me just say this: is that in my view, if we're talking about conventional single main rotor and tandem rotor helicopter, sort of classic legacy aircraft, we're probably at the 90% point in terms of flight control technology. There's not a whole lot of research that needs to be done. But if we're talking about these new configurations, and you see this not only for these military configurations, but also for eVTOLs, I think we're only at the starting gate. So there's a lot of opportunity here for research and for students to learn these technologies and apply them as we go forward. All right, so the next class of aircraft are existing fielded piloted aircraft, which have been turned into UAVs or into drones. You see a variety of them, including the K-MAX, which are mentioned over here, which is so there are a number of these that have been fielded. I'm going to focus on the Fire Scout, which is one that I worked on personally, and along with some of my colleagues. And so there was no physics-based model of the Fire Scout. It was based on a Schweitzer 333, and they had no physics-based model, so they just went out and did system ID. We used Cypher. We extracted point models and made a stitch model out of it. They used demand specifications, which makes sense because it was originally a piloted aircraft. You just took the pilot out and put a computer inside. They designed flight control systems using Conduit. And this is an example of what comes out of Conduit. So these are all the many specs. The top row, the second one on the left, is stability margin. So, for example, you have to achieve a certain gain in phase margin. Classic margin. And the white region is a level 1 region. So what Conduit does is it tunes the design parameters to meet all these various competing specs. And then you have a level 1 aircraft, so it's going to fly well, and we have a very valid model. As you can see, we actually not do it. The simulation and track the flight system very well. And the Fire Scout was designed this way, and it was operationally fielded on 80 ships about 13 years ago. And it's been a very, very, very successful aircraft using these technologies. So the K-MAX, I already mentioned, it also did not have a physics-based model. It used cable angle feedback, so it measures the cable angle relative to the vehicle and feeds that back. Very sophisticated control system. It was also, we did all the simulation modeling, using system identification and Conduit to do all the flight control optimization. It was fielded in a 3-year operational trial and theater. There were thousands of delivery missions to soldiers that needed replenishment of their supplies, and very successful. There have been many other flight demonstration programs which have confirmed that ADS-33 is good guidance for these unmanned aircraft because they are originally, the aircraft themselves are based on piloted control. And basically, the control system is only going to, at best, it's going to be as good as a good pilot. It's never going to be better, probably. So if the handling qualities, we're going to give it good pilot handling qualities, it's going to give it good flight life. And there's also a lot of work on autonomous guidance navigation, like flying on obstacles that's been done by the Army as well. All right. Yet there are many challenges. And one of the key challenges that I want to highlight here is not only for shipboard operation, but for rooftop operations. A lot of these eVTOLs have their concept being going to land on a rooftop. Okay, and that sounds good, and that keeps you off the ground, and you don't have any noise problems and so forth. But if you ever look at some of these high-rise buildings in San Francisco, it can be totally calm at street level, and the flag can be standing straight out up at the top of the roof, and so it's shedding all kinds of vortices. So we have to understand turbulence models for this environment. The right control system design requirements, and the right kind of evaluation. All right. So the next class of aircraft are small eVTOLs for surveillance and for package delivery. This is just a small sample. There are many such aircraft around. Right? And the first application of system identification and flight control design methods developed for large scale and applied for small scale was done by Way. And one of the interesting things we found, and you will find on all multi-rotors, is that the multi-rotor vehicles are dominated by speed stability. What that means is that if you translate forward, if you develop a perturbation in U, you get a very large pitching moment. So the aircraft will pitch backward, and then it goes backward and pitches forward, and it produces a very unstable aircraft. This is very different than aircraft which have flapping motors. Flapping motors, these derivatives are small, and the rate damping is large. Here, there's almost no rate damping. It's dominated by these terms, and it's such a big deal. And it's not only gives you an unstable, very unstable aircraft. So anybody that flies one of these DJI or other quad rotors knows that if you turn the control system off, the vehicle is totally uncontrollable. I don't know if anybody flies small RC drones and multicopters. They're totally uncontrollable, and that's the reason. But not only do these derivatives make them unstable, they also make them sensitive to gust, because if you have a U gust, the aircraft is going to run away from the gust. That makes the aircraft very, very sensitive. So the Army came along, and Kenny Chung and my group led a significant program to evaluate the full range of full-scale technologies that applied to an Iris Plus, which is a small drone about multicopter about a meter across. And one of the things he did was extract the turbulence model and then use that for flight control design. And here, this is the stabilized motor. Anybody who's worked with these, for example, the Tischler system is widely used, and it has an auto-tune mode called stabilize. And this is how it holds hover. Not very good. It's plus or minus 3 feet in all directions. It's all over the sky, right? But now, if you take this model that we've identified using system identification and conduit and optimize the control system, it's like somebody described it as nailing the aircraft in the sky. I mean, it doesn't move. You can make these aircraft fly very well. The problem is not the aircraft, and it's not the control system. It's the way in which the control system is designed. And the articopter is just not a very good control system. It's a very good sensor package, but not very good control. And one of the things that Marcos Barrios and my group did was he showed that with these small aircraft, that the disturbance rejection bandwidth, which I talked about, was critical. That basically, if you turn up the disturbance rejection bandwidth, you basically get tighter and tighter disturbance rejection, and the aircraft is holding its position in small and small. So go from 3 feet down to 1 foot. All right. A lot of work has also been done by Tischler, who was one of my employees and one of my students. Now is a professor at the University of Portland. One of the things he did was validate fruit scaling. Fruit scaling has been around for a long time, since the 1920s. Basically, it allows you to take two aircraft, a small version of an aircraft and a large one that look the same, but they're shrunk. And it allows you to scale all the building control derivatives and all its characteristics. So she did that. So she first thing she did was identify state-space model of a hexacopter, a very small hexacopter, and you can't even see where the ID and the flight data are. And this is very large motion, plus or minus 120 degrees per second. So this is a small hexacopter. And then at the Army, we had a larger hexacopter, and she scaled her aircraft using fruit scaling and the derivatives up to the same size of this large hexacopter, and lo and behold, the dynamics of the circuit. What that means it's a very powerful result. What this means is that you can take handling quantity specifications from full scale and scale them down to smaller size vehicles like eVTOLs or even these small vehicles, and vice versa. You can build a scale model of an aircraft, as long as it has the same geometric characteristics, scale it up to a larger scale. And this is a path forward for companies wanting to develop these flying taxis starting out using subscale models. So this works extremely well. The other way that you can use this technology is for package delivery. So what Anthony Gong did was he identified a model, and that model tracks flight test data extremely well. And then he used this stitch model framework, which allows you to extrapolate, as I mentioned, for changes in mass characteristics and inertia. And say, okay, what happens if you put a payload inside of this box? So the box is fixed. You don't see the aerodynamics, but you know what the effect is the payload inside that box on inertia. You dial that into the model, and you get a prediction line that's this, and then you go out and fly it. And sure enough, prediction line is sitting right on top of the flight display. So that means that this extrapolation works really well. So this opens the door for on-demand package delivery. Amazon comes along and says, here's this package I want you to take and put it on a scale. You measure its weight. You update your CG and mass and moment of inertia. You update your ABCD matrices, and you update your control system. And so that's the concept. So instead of it being an adaptive, real-time adaptive control, which is not deterministic, this is fully deterministic. You get the same answer every time. It's a big deal. And it's a way forward for this sort of application. There are many additional highlights. At the Army, they developed an approach called the joint input output method, which allows you to determine the control authority of individual actuators, individual rotors. So you have some of these eVTOLs with many rotors, and you want to know what their individual effectiveness is. And so that allows you to do that. We come up with turbulence models, and I've worked a lot in looking at how to extend these steady models, which are for a single main rotor, to multiple rotors. There's been some experimental work done as well. Work on very agile configurations. There's work being done to develop a whole set of camouflage requirements like AIAA-SF, but for unmanned aircraft. And then there's an interesting Army program on a fairly large aircraft that carries 80 pounds. We're going to look at physics-based models and systems. But there's so many challenges. These multi-copter vehicles are dominated by these speed derivatives, and it makes them very sensitive to turbulence. So, but you want them to fly in conditions of high turbulence. So that's going to be a challenge. The physics-based models are not ready for prime time. The configuration just doesn't agree with the theoretical assumption. They change rapidly. You go to some of these companies, they'll flight test it one day, crash it, change it, fly the next day. There's no way for the physics-based models to fly. But you can go out and do frequency sweeps and identify new models just like this. So and there's a challenge to come up with these sections. The next class of aircraft is really what's all the rage now, which are this whole family of vehicles called eVTOL for advanced air mobility and urban air mobility, or so-called flying taxis and cars. And these are some of the aircraft that are already flying. So a couple of years ago, there weren't so many; they were just on the drawing board. But now you can find YouTube videos of all these aircraft flying. Here's one in China, and this is one that's still on the drawing board, but it's being constructed right away. There are about 300 of these developers worldwide, and the Bay Area is one of the hubs for it. In fact, the two leading companies worldwide are Joby, which is in the Bay Area, and Archer, which is in Santa Clara. Archer just got a pre-order by United Airlines to order. So this is serious stuff. And you can see that they're all shapes and sizes, including some for package delivery. So NASA has a big research project called the NASA Revolutionary Vertical Lift Technology. They're looking at physics-based models, flight control design, including specifications, and quality requirements, subscale flight testing, and they're developing new physics-based modeling tools. There's another working group, international working group, that's trying to come up with best practices. And there's not a whole lot of data that's been published yet, but NASA is doing some basic research in the vertical motion simulator using, in this case, it's a kind of a generic flying taxis. And one of the things they've looked at is what kind of bandwidth we can get. So here's the handling quality requirements. We saw an example of this earlier. You have to be in this area for level 1. Well, this indicates that if you use collective control, you can meet the requirements. But if you use RPM control, which most of these vehicles these days are using, you're just barely on the level 1, level 2 line. Just barely make minimum quality. So this means that this is going to be tricky to get the handling qualities that we need to be using purely RPM control. And the advantage of RPM control is much simpler. You don't have the moving collective. It's just engine up. And then you can take this model and you can do flight control design. And one of the specs called the OLAP spec, or open loop function spec, is a describing function that basically looks at the effect of actuator limiting on handling quality. And if you're on this side of the boundary, it predicts that you can have pilot-induced oscillation like we saw earlier for time delays, and the other side of the boundary is going to be okay. And what this indicates is that that for this particular aircraft, it's going to be susceptible to pilot-induced oscillation. And sure enough, the pilot flew this configuration, and when he was very gentle on the stick, the aircraft was all behave. And as soon as he became more aggressive, it starts to fight this actuator rate limiting, and the aircraft crashes. So what this indicates is that this RPM control is tricky. It has a lot of advantages, but it has to be used. It has to be applied to that. Okay. So we need accurate, in order to get this right, we need accurate models of the engine and RPM and powertrain, which are really important to get the design right and be sure that you can fly right close to the boundary. And there are big differences between when you use collective only versus RPM, and some researchers are looking at a hybrid solution in which you use both RPM and collective to give you a little more bandwidth out here. Still having the advantages of RPM. There's work that's done in the wind tunnel at small scale. As most aircraft are put in the wind tunnel at small scale. This is to characterize the engine RPM dynamics of one of these quad rotors. So it's a quad rotor, but each arm is a coaxial. This is this TRV 80-pound lifter that I talked about before. So you can sweep in the tunnel. You get a model of frequency domain, and then you can see that the model predicts the response extremely accurately. So this is a way in which you use wind tunnel tests and ground tests to characterize engine models. This is pretty ubiquitous these days. People developing these electric propulsion systems will set them up in a hangar, do a sweep, characterize the aircraft, the RPM response. Because as we just saw in the previous slide, understanding the RPM response is critical to being able to put known qualities and do a control system. There's a lot of work done on looking at scaling from full scale down to subscale and the other direction. So this is work by Chris Yagler from University of Portland. And here, what she did was she took full scale handling quality requirements, used fruit scaling down to her small hexacopter, and figured out where the fruit scale boundary should be. And then tested the aircraft, and sure enough, when you met this fruit scale boundary, you got level one performance, and that's shown here. So this is the fruit scale boundary, and when you within this boundary, and you have the right disturbance injection in this boundary, then the aircraft has got the right precision. And the same thing was done for looking at the closed loop bandwidth. This is for the disturbance response. Same thing was for the closed loop bandwidth. And combine these two together, and then she went on and flew it. When it didn't meet the requirements, so way outside of the spec. But when you meet the requirement, then you have this blue line, very nice flying aircraft, in which the flew it and stayed within the lanes that you're trying to track. So this shows the power of this sort of fruit scaling, and not only take large scale handling qualities down to smaller size, this is eVTOLs are smaller, or upscale from smaller scale things. Gives you that path in both directions. And one of the very interesting results that came from Mark Lopez was on an aircraft that we built for DARPA. This was an aircraft that allowed you to configure from 4 rotors to 6 rotors to 8 rotors, but all of them same footprint. So as you went up in the number of rotors, you started getting interference between the rotors. And the interesting thing was that when you identify the control derivative associated with each of the individual rotors, that when you start to get closer, you get from 4 to 6, and it's still okay, but then you go from 6 to 8, and the control power drops by 10%, and if you include the extra inertia, it actually drops. So that means that some of these configurations that have the rotors closely stacked together are going to have a lot of mutual interference. It's very difficult to model this. We were able to extract from flight test data, but you really want a design code which we can. This was a big deal. And it speaks to some of these configurations that you can find online. So you have just a ton of rotors. There's a lot of additional work. There's work on physics-based modeling of these vehicles, system ID to extract linear LTI models from the complex simulation. Say turbulence models are talked about. Extensive studies that show the value of the AIAA-SF, even for these eVTOLs. Very strong role of hardware-in-the-loop testing, and a great success of using subscale demonstrators. So there are companies who have published their results, like Joby and others, that have the first thing they did was fly these subscale versions of their eVTOLs flying cars, and it worked out a lot of the bugs in terms of flight control and configuration, and then full scaling stuff. And there are many videos of all these aircraft. You find all these online now, just in the last year or two. But there's no hard data available. Right? Nobody's going to publish their data. So that's tough. But they're out there, and I can assure you that if you're graduating now in the government job market, once upon a time when I came to the Bay Area, the only place to work in aeronautical engineering was NASA Army. Today, there is just this buzz of activity. Probably the Bay Area is the biggest single developer of these eVTOLs, and they're all looking for flight control. So they have a lot of choices. There are many challenges, and these are various kinds of configurations. There are many unique configurations, so it gives you a very strong role for an invitation to update the physics-based models. There's a lot of structural coupling because these vehicles have to be very lightweight, and a lot of times their rotors are way out on the wingtips, and so there's a lot of structural flexibility comes into play. You want to land them, as I mentioned, on rooftops, tend to be over-actuated, so you have to worry about control allocation and damage configuration. So it's a great research area still. All right, so we're getting toward the end here. This slide will summarize all the various challenges across all these modern aircraft. I've been talking about the future aircraft and looking at the solution space. So the first area is the need for handling quality requirements, and a good solution space is going to be these new handling qualities, spec populated with some of the new flight test data, and perhaps parametric studies from research institutions that have suitable aircraft or simulation experiments. The next area that needs to be addressed, the challenge is validated physics-based models for a wide range of configurations. And here we can augment things like the element of higher order aero, like its advanced inflow dynamics and CFD, as part of them, as well as these simple models of turbulence. The next challenge is these highly compressed development schedules. When they first started talking about eVTOLs or flying taxis, this was maybe 10 years ago, and they were going to be, they said they're going to be operating in the next 4 or 5 years. Well, that was 10 years. and they haven't even made FAA, nobody even knows how to get through the FAA process. So they're going to be a while. So the only way they're going to get out the other end of it is use tried and true methods. System identification early on to document the vehicles, use subscale demonstrators and food scaling to try to cut the development time, because it's going on and on. But now they're saying the vehicles will be in service in 2 years. I don't know. I got a great story. We'll see. There are many challenging flight control problems, many unique configurations, and here's where tried and true, well-vetted flight control architectures like explicit model following, and the multi-objective documentation is going to work very well. So each case, we see that the technologies which I've covered and have been developed over the last 30 or 40 years are going to hold us very well for these aircraft concepts. And finally, there's a need for government-owned flight test beds as well as simulation. Overall, the methods, tools, and lessons learned over the past 30 years are going to be the key to developing flight dynamics and control for this next generation aircraft. So as students should learn these methods, because when you go interview, I can assure you they're going to say, what do you know about system IDs? What do you ever use cycle control? What do you know about flight control design? What do you know about handling policy? And I ask you that. So learn a little bit of it, whether that, read a little bit in my books or take one of the classes or try some of the stuff. Lessons learned. Okay, and here I want to speak to some younger folks here in the audience. One of the things that I learned early on was the only way you're going to advance technology is through collaboration across a wide range of vehicles. These are just some of the vehicles that I worked on in my career, probably working about 100 total. And that's the only way you're going to move things forward. If you always stay focused on one configuration, the whole career, you're never going to move it. You have to have possibilities. That's one big lesson. The next big lesson learned is you got to turn your theory into usable software. In the old days, people would come up with an equation. They would show that it validates the data and say, okay, now it's up to you to develop the software. It doesn't work anymore. The software is very sophisticated. And so we turned system identification into a software tool called Conduit, and I did a book on it. We came up with lessons learned in flight control, and I documented that in the book, as well as a tool to do automated parameter-based optimization for control system design. And again, wrote a book on that. And then there's another tool just using a stitch model, which allows you to take the point model and make fine tune. So we have not only the software, but the textbooks and the training books. It's the only way you're going to move them. So if all we do in research is publish a paper and say, okay, now you try it on your own, you're just never going to pick it up. It's just too sophisticated. You have to give them the software that goes with them. Now some more general lessons learned. There are many new configurations out there. In my view, we're in the golden age of flight control. Maybe there was a time when flight control people had a hard time finding jobs. You go on LinkedIn, the number one requirement is for flight control. So I say, I'm a flight control person, of course, I say study flight dynamics control. Learn the basics. Learn F equals MA. Learn stability margins. Learn feedback theory. Take courses from Mohammed. And it'll hold you in good stead, because these companies are all looking for people that understand the flight control. They're hard to find, and I have to go around. We have all these companies. Used to be like 4 prime Rotorcraft companies and other aircraft companies. Now there's 60 in the Bay Area alone, 40 in the Bay Area alone. Sorry, just in the Bay Area alone. They can't get. It's a buyer's market. So the next thing is that flight control is highly multidisciplinary. You really have to understand the control system. You have to understand the vehicle dynamics. You have to understand handling policy. And all these things talk to each other. And so you have to take some courses which cover all these areas, learn a little bit about each of these. Okay, and I know that there are courses here that are taught. There are also short courses that are given and things like Rotorcraft. System ID is probably, and you've seen it over and over again, we talk about how it's used, it's probably the single most important integration tool for cost saving in flight control. It's something that you really should learn. Advancement is a nonlinear process. Sometimes it's cost realization from the fixed wing community to Rotorcraft. Other times you develop something that sits on the shelf and you go back and review the literature. You go, hey, somebody tried this 20 years ago. Let me try it again. Maybe things have changed and it's faster and faster. So it's not obvious a lot of times where you're going with these. Fielded applications can take a long time, maybe a 33 to 20 years. Second conduit took between 10 and 20 years each. The long development cycles for big breakthroughs, but eventually we get there. Collaboration is the key. Interacting with other researchers, going to conferences. You know, it's not only about writing the paper, but it's meeting people and getting your name out there, and you get what my colleague in Germany used to call the aha moments. You get away from your computer and you go to a conference, and all of a sudden you go, oh, that's how we did it. Maybe I can apply that to my problem. Maybe that's. And true technology transfer takes a lot of effort. You gotta have quite validated methods, papers, good courses. And flight control advancement requires us to be more research driven and less strict. Finally, some acknowledgments. I had a lot of mentors in my career. I was blessed by that, and that's really key to all you. And I encourage you to reach out and look around and ask. Try to find people. Go to conferences and go up to somebody and say, "Tell me about your career. How did you get doing what you're doing? What was your career path?" Because as students, and when I was a student, I had no idea what a career in aerospace, especially a career in flight control, meant. No clue. And so I had many terrific mentors over my life. Probably my dad was my first and most important mentor, and he would always say, "If you're good at what you do, you can always find a job." When I started in school, the aerospace industry was in full decline, and I was worried about studying aerospace. I said, you know, if you're good at what you do, you'll always be a job. And I got out, and the aerospace industry was booming, and I needed more job opportunities. There are many folks here, and I encourage you to reach out and find mentors throughout your life. Wherever you are in your career, find people that have been there before that can help you not only with technical decisions, but also career decisions. Aerospace and aeronautical engineering has been my life since I was 12 years old. I tell people who want to get a PhD, I say, you know what? If you were born with a airplane in your mouth, get a PhD. If you weren't, and you can study robotics as well or mechanical engineering, you know, you may want to be broader. But it's been a passion of mine since my earliest days, and so and it's been possible through my career in the Army and many research collaborations in the last several years, many research collaborations with industry. Now that I'm working on my own, and over a very long period. So with that, I want to thank the society and especially thank Eric Wall and for inviting me. There's a lot more information. This whole presentation is in this paper. There are a lot of updates that are not totally contained in this, but I think this lecture has been recorded and is available. Please reach out to me. So my job now is to support and mentor industry teams trying to apply methods, fundamental methods that I developed and tools to unique aircraft, and try to help mentor the workers, the young engineers, as well as the companies through these revolutionary projects. Also, okay, so with that,
one thing, we'll get to Q&A in just a moment, but I did want to take a moment to thank Dr. Ayubi and the Santa Clara Student Branch of AIAA for hosting us and giving us the space and helping to connect us with Dr. Tischler. So thank you very much. And also to IEEE as well for sort of co-sponsoring and helping to advertise this event.
Good.
If you could, since you're closer up here, if you could repeat whatever questions for the people.
Yes, I will do.
And for the people online, please put your question into there's a Q&A box, so not the regular comments, but a Q&A box, and I'll read them out.
Okay, excellent. Yeah. Yeah. Please.
So my question is about the Amazon example where the Rotorcraft is packages
Yes.
can play differently.
Yes.
say that when the delivery has to be made, obviously the data is there.
Yes,
It has to be different model parameters.
that's right.
Once the weight drop, they have to select the program.
That's right. That's right. Exactly. So what the student did was actually fly a simulated mission. Exactly. Looked at what happened if you reconfigure it versus you just sort of try to design it with enough robustness to handle it. It's much better by you would basically have a lookup table of the whole system parameters that was automatically populated by weighing the load, and then you know what it was, what the baseline was at no load, and as soon as you drop the load, yes, it's again called deterministic reconfiguration as opposed to being online. People were going after adaptive control for a very long time. This is adaptive control, but it's deterministic. You always get the same answer.
I wonder if you can comment on one of the weird things about rotorcraft control. I came up with a fixed wing world and I saw this. What? It's called gyroscopic precession.
Yeah.
So if you want to make a control change the pitch of rotor blades, you put that in, but it's not going to be effective until 90 degrees later. What? So you just automatically account for that weird behavior?
Yes. So basically, what is the rotor system is the second order system, and it's being controlled with a one Pareto control. So cyclic control is the sign. And because you're exciting it exactly at the natural frequency, if you think about a second order system at the natural frequency at the phase. Yes, all these models account for this. So what that means is that if you want to let the aircraft roll, you actually put in an input that's 90 degrees of pivot. You think it's a pitch input, but it actually won't take effect. And then one of the things that makes the rotorcraft.
Let's I'll answer this one. Let's do one line.
Yeah.
So recently we've heard like the nation story of
Yeah.
yes, and over that incident and what made the video into operation again. And that it's an article that it's on online saying that the operational parts. So what do you think what would you say is like the next steps to ensure like safety?
It's out of my figure, but usually these kind of problems are operational and aerodynamic problems, not really control system problems. And a lot of the problems in the B-22 in the early days had to do with what happened when you had a fast descent and you kind of was called that swing state in which the air got recirculated. It made for controls of lose their effect. A lot of these problems have been overcome with the advanced made by the same manufacturer, built the B-22, but 20 years later. So they fixed a lot of those problems. Well, I think that's where the long-term future is. I'm sure that they'll get back to service in the future. It's very effective aircraft. It's had some action. That's also to some extent that makes the rotorcraft. They have a safety record that's not as good as it's swing, but they're operating in environments. Yes.
Okay, so we got a couple questions online. First one is for slide 30.
Read the name or did it have it?
It's I'm going to mispronounce this, but here, let's do this. Answer like. Okay, so slide 30, which I just pulled up here.
Okay.
Let's see. It says I have not read the paper, but after the model parameters were changed using the flight data,
Yes.
was the resultant model then reevaluated on any new data?
Right here. There it is. That's the result model, and it plays right on top of it. But what you so basically we identified the model, we identified the physical parameters that were necessary to track the flight statement, and then dial those into the physics-based model, things like effective pitch offset, inertias of the blades, flattening frequency. And then once you dial those back in as physical parameters, the updated model tracks the flight data perfectly.
Okay, thank you. And then let's see. Next question is, what is the best or simplified advice for new undergraduate engineers entering the field?
Learn the basics. Learn, you know, look, when I was an undergraduate and somebody showed me Boeing flights, and I really need to learn this first to do. And so learn the basics. When Professor AIAA says, you know, you have to understand the root locus rules, you have to understand the root locus. These are things you're going to learn. If you're going to get into your first job, they're going to expect you to know this stuff. And yes, MATLAB is out there, but MATLAB can give you garbage in and garbage out all the time. So you have to have some physical intuition. You have to learn the basics. Take a advanced dynamics course, you know, and Newtonian dynamics. Take a course in simulation modeling with Simulink. Learn how to use Simulink. Learn some MATLAB. These days, everything is written in MATLAB scripts. And get involved. And I know you have a tool here. You have what's it called, a fly contest. Build the fly. Design meeting. Yeah, those sorts of things are going to give you a lot of experience applying this and really getting. And then when you go out to the interview, you'll be able to speak intelligently about this. Take short courses. If it's not being offered, if it's a course that's not being offered, then take a short course and many of them around.
Okay, back to the room.
Yes, sir.
I would like to mention cross-pollinations.
Yes.
So I guess that applies to different aircraft types.
Yes.
But what about different aircraft and different grades? So I was young, I was going to the trainer.
Yeah, I mean, for example, the chief of flight control working on the Bell Advanced Tilt Rotor was a fixed wing fighter pilot, and you know, there's this huge amount of cross pollination when you take. So I came from the fixed wing world. I didn't know what a helicopter was. When the Army hired me, said, "Hey, why don't you work on a rotorcraft simulation, apply it to this X-215, which became the V-22?" I said, "Sure, I'll try." So I took the methods I had learned at Systems Technology Incorporated, experts in fixed wing for the most part, and said, "Okay, well," they brought me. They said, "We want you to validate the simulation model." I knew what I knew from where I had worked, and I cross-pollinated. I took their methods, which had never been tried on a rotorcraft, and said, "Hey, this is the way we did it on fixed wing. Let's try it on a rotorcraft." So those are the things. Getting out. That's why I say whatever it takes. Getting out to a conference and seeing what other people are doing. Getting, you know, reading the literature. Getting these ideas. The cross-pollination is so important. You know, and I think, you know, there's nothing like, there's not, you know, you got to talk to your colleagues, but you also have to get out and talk to others. Yes, sir. No.
Thanks, Mark,
Sure.
for explaining that.
Sure.
So I have a comment question. The comment is basically, it's going to really reflect the settles. I think you may want to explain with X-26. Photo suppression control schema as a quick as a function. You know, they start out.
Tell the folks what an X-56 is.
X-56A is a body. It's a body figure photo. It's a design unstable. It has a first weekend model.
Very flexible machine with a lot of surfaces to control.
Right. So if design is unstable, so the asset side we want to develop against affecting control because we stabilize the vehicle. So they developed start out with the space model using gas to get the space frame model, and then use the space frame model to design a controller. They would get flight test and collect flight test data, and the data becomes massive.
Never does.
So never does.
Never does.
And so they decided they want to do system. do a system ID that becomes function design first question. We have.
It's beautiful, it's beautiful.
Yeah,
example.
so that's what I was doing.
I mean, the people who learn these tools, especially people, my experience is people who train and learn system ID, they become the magicians at wherever they go. Because you talk about cross-pollination, because it's like a stethoscope, or a microscope. It gives them insight into what's going on in a way nothing else can. And so these people become the go-to people for problem solving, just like described. Because Nastran, it will give you the answer out to three decimal points, but it'll have a wrong sign. So it's right, it's not a good answer. So you have this sort of super accurate model, but it's wrong. And so system ID will allow you to extract those same parameters. You can update your Nastran model or replace your Nastran model. A lot of times, Nastran model is the first step, because you need something, you need a way to get going. People say, well, I can't get system ID if I haven't flown it. That's true. So you need a physics-based model in Nastran to start with. And the very first thing they do, so I remember watching a flight test of this, of course, the aircraft, a new fly-by-wire, one of these advanced vehicles, and I saw a video. The very next day, they put it up online on YouTube, and the aircraft looks like it's wobbling. And I called the director of the flight control chief. I said, hey, what's going on? Your aircraft seems like it's wobbling. I said, well, the very first flight we do, very first thing we do, system ID. And that's true in fixed wing. Very first thing. So again, learning a little bit about each of these technologies. That's a great story. I knew that they used it in Armstrong. They had used it on Ford's plane. That aircraft.
So the second point I want to make is we have a way where they buy the Boeing most from attending the flight test we do. So the industry folks basically said, well, why don't we ditch the fixed space model and go with system ID model? Why don't you make an effort to improve the fixed space model so that we know how to apply this correction to the space model?
Right.
So that we have to always use
Right.
So I thought that was a point well taken.
Yes.
So,
I mean, you can do both. It's not either or, right? I mean, you can do both. I just wanted to get to the end here, but yes, I mean, you should be able to update your physics-based model. But in the end of the day, what most companies do is they walk away from the physics-based model because they have a model which is much more accurate. And we've done it both ways. So I agree with that. Other questions? Other comments? Sure. Yeah. Yes.
well, I know I wanted to ask, do you think complexity you think that there's a benefit?
Oh, everybody's driving toward full autonomy, and these flying taxis. Originally, when they were going to field them in 3 years, they were going to be fully autonomous. Take the pilot out, right? We're not there yet, but that's still their intent. And I just saw where the DoD, when they dropped and canceled the piloted Apache replacement called FARA, which I mentioned, they're saying that now it's going to be, it's sky wars, it's drone warfare. So yes, there's going to be a role for small and very large UAVs, without a doubt. I mean, you see them everywhere. You see them in all the modern conflicts, as well as But look, people ask me about this, and it's a good question. But okay, we didn't. 5 years ago, we didn't think there were going to be autonomous cars. Now there are robo taxis in San Francisco that regularly get stuck. And they need somebody in the ground station to say, oh yeah, it's a construction zone, you should go around. Or we didn't expect this, and then every once in a while they hit a pedestrian, and that's happening. So now we're going to do this in 3D. So we have maybe more space, but there's nowhere to fall off the road. So is it coming? Yes, eventually it's going to be reliable. Is it today to tomorrow. But it's coming, and it's something you should be aware of. I mean, something that, for students to learn a little bit about outer loop guidance and navigation, and everybody's saying that AI is gonna play this role in the outer loop, and maybe it can. In fact, I read an article about there's a whole big research project with DARPA to develop autonomous fighters. And what they say is that they've had games where they have a pilot fly against one of these autonomous things, and they say that if the autonomous aircraft beats the pilot, well, probably can handle a lot more G's than the pilot can go on, and can make decisions. But on the other hand, I don't know, some of the decisions about where to go and what to do, it's more than I think the AI. We'll see. I mean, never say never, right? We expect them to have ChatGPT and now can do it. Other thoughts, comments?
I was going to say it's going to be interesting pilots for these results because it's pretty uncomfortable. How someone justify that.
Right. Yeah, I mean, it's a challenge because the pilots now that talking about getting our people who used to find video games, not so much sticking with it. So, right. Probably not. That's the thing, is that you're always going to be a whole pilot, but it's coming. There's going to be some mix of automation. There's no question. I mean, if you look at some of the conflicts that are ongoing now, military is always the leading edge, right? Eventually, all the autonomy stuff that we're seeing now was all originally developed by DARPA and the military, and now it's being developed by students. So it's always that way. But, there's just everything. I mean, cheap drones are having a huge impact on the applications. They will, they're already being used for things like photography and for real estate. And they're everywhere. You go out and buy very sophisticated drones for another question.
Yes.
Just in your experience, what the most challenging situations and then what you wrote that. That's a good question. I think, in my view, an underappreciated problem is this idea that we're going to land these air taxis on rooftops. That's when the rubber hits the road. When they're up and away, and you don't have to be that precise. It's one thing. What's happening, so again, you go to San Francisco and you see the flags standing straight out on the top of this building, you're shedding huge amounts of horse. And now they want to land on top of it, right? And they can't afford to go around and come back, when it's calm. So the idea of these air taxis, if you're not familiar with them, is typically have about a 30-minute flight time. The idea is that you go from the Control Valley to San Francisco without taking decks and other people that they don't want to get stuck in traffic. So they have about 20 to 30 minutes of flight time and about another 10 minutes spare. Well, they got to live with what they're living with, and they're all, the idea is it's going to be landing at altitude and rooftops so that you don't have you have the noise problems because the companies are talking about thousands of these things in the air. They'll just show traffic jam on 101 and go, now we're going to lift these vehicles in the air. Well, first of all, we're not going to all these thousands of vehicles in the air. But that's the idea. And it's always this difficult environment of landing environment. I think that's where things are going to get. Where you really have to have good models.
Seems to be. Any last questions online?
Which late,
Yeah.
people had signed up in Turkey and Asia. the middle of the night there, so I appreciate great response. Again, the paper is available. You can find it, it's and I will provide a PDF, so you have all the registrants, right?
Mhm.
I will provide you the PDF of the paper. So it's a couple of years old, it doesn't have the most recent results that I showed, some of the air taxis, but it has a great amount of useful information. And then reach out to me. My job these days is to see that the methods that my team developed over the years carried on and used and advanced. And that takes mentoring, and that's what my career now is providing support and mentoring to companies and persons trying to train their staff, young people, and working engineers. Reach out. I mean, there's nothing I like better than somebody said, hey, like now, say, hey, I tried this. I mean, there's people using, I go to a conference and sometimes I sit in the conference and it's, this paper used conduit, this paper used ciphering. It's like, you have a sense of the sense of things. And so, at this point in my life, I love to hear what people are doing and help people use these methods. Thanks again. Thanks you for inviting me.